Okay, seeing none, I'll keep moving on to the next one. So now, for the time being, let's assume we have a model and we decided this is our model, acknowledging that there might be other ways we could have built the model, but now we're having a model. Now, the next level of uncertainty comes that you have your parameters in your model, and to be able to run the model and analyze it, um, we need to supply values for these parameters and also the starting conditions. So often when I say parameters, even though the things that change we call variables, the starting conditions of the variables are, for all intents and purposes, also a parameter, both when we do fitting or when we need to explore them here. So depending on how much knowledge we have about the system, we might or might not know these parameters to a lot of precision. Sometimes we might not know them at all. So, if you study some pathogen that has not gotten much attention, let's say these were bacteria, and you study some kind of bacteria that no one's really looked at, you might not find anything for the growth rate, that parameter G. You might have to look at a bacteria that is somewhat similar and say, oh, okay, we know that E. coli doubles every 20 minutes and our pathogen is kind of similar, so let's make it 30 minutes, right? But sometimes that's the level of detail you have, and that's what you have to live with. If you look at something that's better studied, you might get results. But again, they might be limiting. You might find the growth rate for TB, but it comes from an in vitro experiment. And you really want to model TB in vivo. It's probably better than nothing to take that in vitro data, but it's it doesn't fully apply to your in vivo system. So that's the thing. We often don't know the parameters too well. And so obviously, as the parameter values change, the outcomes change. So how do we deal with that? One thing we've already looked at, if the model is simple or there's only one or a few parameters we're interested in, we can basically run the model at different parameter values. We can look at the outcome that we're interested in for each of those parameters and systematically explore the model. Now, that works okay if you don't have too many parameters, but once your model gets big enough, you can't really do that anymore. Also, sometimes you're really not interested in all the parameters. You have a certain parameter that you're mostly interested in. So, for instance, it might be related to one component of the immune system in your model. Let's say you want to know how production and decay of IL-10 affects the outcome, and the other components you're not that interested in. So then what do you do? Because you can of course fix all the other parameters to a specific value, but again, you might not know them very accurately. There might be uncertainty in those other parameters. And then of course there's the other option where you might want to make predictions. And if you want to make quantitative predictions, you should attach some kind of uncertainty to your predictions. And any uncertainty in your parameters will propagate through the system and lead to uncertainty in the outcomes. So you should somehow quantify that when you're trying to make predictions. And so what you can do for that is an approach called uncertainty and sensitivity analysis. The idea is that you change some or all of your parameters over a broad range, and you, for every set of these parameters, run your model, compute your outcomes, and then you can, instead of now getting a single estimate for your outcome, you get a distribution outcomes because you have a distribution of inputs, your parameters. So basically, when you do uncertainty and sensitivity analysis, you basically do them at the same time. It's just asking different questions. The uncertainty analysis asks, given that I have uncertainty in my inputs, how much uncertainty is there in my outputs? The sensitivity analysis goes one step further and asks, okay, how much does each one of these inputs contribute to the uncertainty in the outputs? And as you'll see in a few minutes, you do that at the same time. It's just how you then look at the answers that gives you the different answers to different questions. So you start by determining ranges of uncertainty for each one of your inputs. It could be that some of them you are pretty confident you know them. You know that these cells divide every hour, and that's pretty accurate. So you might say, I keep this fixed. Then there are others you might be very uncertain, and you just know, okay, it can't be lower than this, and it can't be higher than that. and you just specify a range and say within that range I have no idea, so it's could be a uniform distribution. Other times you could say, okay, I know it's around a certain value, give or take some spread. So you could choose some kind of distribution. Normal is not that ideal because most of our parameters are positive, but something like a log normal or a gamma distribution, or if you have some between 0 and 1, you could draw from a beta distribution. So some kind of distribution where you can draw from. In practice, quite often just using uniform for all of them works pretty well. It's conservative because it allows the extremes to be sampled more, and usually the results don't change that much. Of course, there's a level of subjectivity because you're deciding what these distributions should be. Of course, you want to choose those based on what you know from the literature, but the honest thing is there's fiddling involved. You know, if you choose certain ranges and your outcome doesn't show enough spread, you might decide, oh, I'm actually not that certain. You change it to make it wider, or you do it the other way around. I once reviewed a paper, just a side comment, that was a population level paper, and they looked at the impact, the potential impact of a drug, and they did uncertainty and sensitivity analysis. So that was nice. The problem was that they predicted that the drug had impact anywhere between 0 and 100%. So I commented that it was nice that they did that. However, the results were not that useful because if it meant the drug could do anywhere between nothing and everything, not sure what we've gained from that. So of course, they could have changed their input ranges to a smaller one and tried to justify this. So anyway, you pick your distributions, you run the model for each of your sample, and you record the outcomes. And then you can plot the distribution of outcomes. So I already mentioned that. You choose distributions for each parameter that you decide you want to vary, and then define those. And then you need to sample your parameters. The sort of two naive ways would be to either just completely randomly sample, but that's not very efficient because there might be just by chance ranges that you're not sampling. You know, let's say you know one parameter is between 1 and 10, and just by chance you don't sample anything above 7, so the whole 7 to 10 is not sampled, so that wouldn't be so good. Another one is to basically put a grid over the distributions and sample out of each box in the grid. That's kind of the middle one in this figure. That gives you very good coverage, but you also need a ton of samples, and you might not be able to do that, especially when you have a lot of parameters. And then there are methods that are basically doing sampling efficiently, and the popular one is called Latin hypercube sampling. Basically, they make sure they draw values from the space of parameters in a way such that the whole space is covered while at the same time being efficient. It's really not too important, I think, unless you really want to get into that to understand more how exactly the sampling is done. If you're more interested, there's the package LHS, and you can look at the documentation. It tells you there's different forms of doing that kind of sampling. So then what you do is you sample over your parameters. So now for every time you run, let's say you do 100 samples or 1,000 samples. So you have 1,000 sets of parameters. Each time for each parameter, they're drawn from the distributions that you think are reasonable for it. You run your model, you record the outcome, and then at the very end, instead of now having just one value for the outcome, you now have a distribution. So in this example, it doesn't really matter what's shown here, but you have some kind of scenarios on the x-axis. In this case, it's interventions on the population level, and then some outcome of interest on the y-axis, in this case, reduction of deaths. And each one you can see is now a box plot, because for each of these scenarios, we sampled the parameters, ran it, we got outcomes, and you see there's a distribution that, sometimes for the intervention one, for instance, it predicts that it's anywhere between roughly 25 to 60% reduction of deaths. So this lets you capture uncertainty in the outcomes given uncertainty in the parameters. You can go one step further and now say, okay, now that I know that there's uncertainty in the outcome, which of my model parameters influences that uncertainty? It could be that all the parameters contribute equally. More likely, there are some parameters that are strongly influential and others that don't make a lot of difference. And for that, you can do sensitivity analysis. You take exactly the same data, only now instead of doing something like a box plot, you're now plotting that parameter of interest on the x-axis and the outcome on the y-axis. You see these kind of clouds of distributions, as you see in that figure here, because while you're varying this one parameter, all the other parameters are varied too. So you see these clouds, but in general, what you should see is if a parameter has an impact, there should be a pattern. If a parameter has little impact, there isn't much pattern. So in this example down there, that parameter beta, there seems to be a clear pattern that as that beta goes up, the outcome goes down, while for the other, the one at the bottom, there seems to be not too much of an impact of this parameter. You first always want to do these plots because you want to see if what kind of pattern you get, if it's a monotone one, if it's a linear one, if it goes up and then down again. That can be of interest, and it's also important to do that even if in the end you don't want to show scatter plots. You can easily see that you can produce a ton of scatter plots. If you have 20 parameters and let's say you have 3 different outcomes of interest, that would give you 60 scatter plots. No one wants to look at 60 scatter plots. You can stick them in the supplement, but not in the main text. So you might want to show 1 or 2, but then after that you can summarize a bit more concisely. And one way you can do that is looking computing correlation coefficients. So basically, just for a moment, forget about that this came from a mechanistic model. Just assume there's something on the x-axis and something on the y-axis. And want to see if there's any kind of correlation. And so you can compute a correlation coefficient, and that will, in one number, basically summarize the impact of that parameter on the outcome. Because for our models, there's no reason to assume that there's a linear correlation between some parameter and an outcome. It's often better to use rank correlation coefficients because the standard correlation coefficient assumes linearity. And then even better is partial rank correlation coefficients, because here you vary all the other inputs at the same time. And so the partial rank correlation coefficient tries to adjust for that and saying, okay, what is the impact of this one parameter on the outcome, given that the others are also varying? And there are routines in R that basically compute those for you. And so you get then a single number for each one that you could report. And a large number close to -101 means that parameter has a strong impact, and a small one means it has little impact. So this is an approach that is fairly easy to do. There isn't much more to it than just sampling, running your model multiple times, and then you can report that. Of course, again, keep in mind, this is given that the model you built is correct. So, if you have a distribution that says, okay, the outcome is somewhere between 25% and 60%, that's for this model, given uncertainty in parameters. If I build a different model, even if I assume the same uncertainty in the parameters, I may get a different distribution. So that's important to keep in mind. I feel sometimes papers, especially on the epi level, that are published in the literature are overselling their results. There's a false sense of accuracy because they did that sampling and they get a distribution, but really it's only contingent on that underlying model. One thing you can do then, you can report it. Another thing you can go further is that, if you did the sensitivity analysis and you find that certain parameters are very influential, you might say, okay, this is a parameter that's either important to intervene. If you had something that was reduction in deaths, or within host situation, the total pathogen load, you can say, well, this is a parameter we should try to intervene. Another one is for your model purposes, you could try to find more data on that, because if it's influential, you want to know that as precisely as possible. On the other hand, if you have a parameter that has almost no impact, you could say, well, maybe I can actually simplify my model and just kick out that process. Sometimes that's possible. It might give you a hint of certain parts in your model that are actually not contributing to the outcomes, and therefore you might be able to ignore that. Keep in mind, however, that it depends on the outcome. If you change your question even with the same model and look at different outcome, let's say you had a question about the peak pathogen load But then your next question was at the steady state of the immune response. Exactly the same system, different question, different parameters could now be impactful. So you need to be careful with just kicking out parts of the model. They might only be not important for that specific outcome.